In this video, we're going to discuss a trick for solving systems at first order by raising them to higher order, which is the traditional method for solving linear waves in introductory classes. This is not as robust as the determinant method presented previously, but it is useful for some systems. We'll illustrate it here using our fully compressible linearized equations at order epsilon for a constant coefficient system. This was our system where we took the t0 to be a constant, and we took that the gradients of t0, and the gradients of the log rho density, log rho 0, are themselves 0. So this constant coefficient system, one set of solutions that we're familiar with seeing for the linear wave acoustic equations are those shown at higher order. The version that we're most familiar seeing, the higher order equations for waves, for linear waves, take the form of a second derivative in time of our quantity u minus the sound speed, the speed of the wave squared, times the second spatial derivative of our quantity u. So we're used to seeing wave equations as being second order in time and second order in space. And the question is, how is our system of first order equations related to this? How do we take our first order system of equations and transform it into the second order system? How do we take our first order system here of 3 equations in 3 unknowns and transform it into the second order system? And why do only 2 of the time derivatives survive rather than all 3? Well, we can start doing this by taking our momentum equation and taking its time derivative. So we take d by dt of our momentum equation. So this is d by dt of u plus r times the gradient of t1 and r t naught times the gradient of log rho 1. And this is all equal to 0 for our linear equations. Now, the important thing is that only our variables t1 and log rho 1 and u1 here, they're the only things that have time derivatives. The constant coefficients r and t naught do not. So as we propagate this equation, this time derivative through, we get the second derivative in time of u, and we get r grad d by dt of t1, where our time derivative propagates through the spatial derivative to hit t1 since they're independent, and r t naught grad d by dt of log rho 1, all equal to 0. Now for this extremely simple system, we already know the solutions to d by dt of t1. This here, this is given by the temperature equation, and this is given by minus gamma minus 1 times t naught times the divergence of u. And likewise, d by dt of log rho 1, this comes from the continuity equation, and this is just minus the divergence of u. As we simplify the system and gather some of our terms, what we get is that d by dt of u, second derivative of u, minus, from our first term, gamma minus 1 r t naught, which is constant, so it propagates through the gradient, grad of the divergence of u, and then minus r t naught, the divergence of u, is equal to 0. Excuse me, I forgot my gradient of the divergence of u when I substituted my divergence of u into my gradient operator. Now, if we collect our terms and keep track of all of our signs, that's the real hazard in this, is the large opportunities for sign errors. We get that d by dt, second derivative of u, minus gamma r t naught times the gradient of the divergence of u is equal to 0. So we've taken our first order system, and by raising the temporal order of the momentum equation by taking its time derivative, we've been able to then create this familiar second order system where we have the sound speed of our waves, sound speed squared. We have this second gradient term, which looks like, it isn't always exactly equal to, but it is for 1D, looks like the gradient, the Laplacian of u, and then this is our second time derivative. And this all looks like our familiar higher order system for our waves. To double check that this yields the same solutions, let's calculate the dispersion relationship. So we'll take, again, that we have our linearized perturbations u1, and that this scales as e to the I omega t minus I k x. What this means is that our second derivative operator, second time derivative operator, this is equal to minus omega squared, and our gradient of the divergence of u operator, at least for one-dimensional waves like this is minus k squared, because the two derivatives in time bring down I omega twice, so it's I squared omega, which is minus omega squared, and likewise for the spatial gradients. Now, if we substitute these in to the equation above, we find that we get minus omega squared u, and then we get minus gamma r t naught times minus k squared on u equals 0. Or, simplifying, we get that, or our dispersion relationship, we get that omega squared is equal to gamma r t naught times k squared. Here again is our sound speed squared, and this dispersion relationship is the same as we found using the determinant method in our previous video. Now, this system works very easily. This is what I would call substitution into the equations, but it is fraught with opportunities for sign error. The determinant method prevents some of these sign errors, and the determinant method is also simpler to extend to more complicated physics. The advantage of this method is one that you have probably seen, and it's one where you can figure out a way to find the solution if you can't remember your linear algebra. But if you can remember linear algebra and the power of the determinant method, that will allow you to solve a much broader class of wave problems and to do so with fewer errors.